Hello everyone. Today I will be presenting our paper, DenseNets Reloaded, Paradigm Shift Beyond ResNets and ViTs. The difference between ResNet and DenseNet is quite simple. While ResNet uses skip connections with add operations, DenseNet uses skip connections with concatenate operations. This subtle difference brings about significant changes at the macro-level architecture. This figure illustrates the structure within one stage of a DenseNet. The X1 feature, after passing through the H1 feature mixer, is combined with the input feature X0 before it is fed into H2. Similarly, the input to H3 is a concatenated feature of X0, X1, and X2. By concatenating these features, DenseNet needs a large amounts of memory due to a large size intermediate features. DenseNet has strong capabilities due to the concatenate operations. It shows impressive results in terms of accuracy relative to parameters and flops. However, the latest backbones are all either ViT or ResNet. Why did DenseNet fail to achieve a paradigm shift? The first reason is its high memory consumption. As the growth rate increases, the intermediate tensors exponentially consume more memory. As we can observe from the table, DenseNet 161 shows similar performance to ResNet 101 but requires significantly more memory. The second reason is low scalability. Increasing the image size significantly raises the latency and memory usage compared to models based on residual connections. We conjecture that concatenation is a very natural operation for increasing the rank. According to ResNet, if the number of output channels increases significantly compared to the number of input channels, the average feature rank is getting lower. In the case of DenseNet, the feature size increases slowly by the growth rate through the concatenation operation. Still, many studies are constructing networks using concatenation. Most of the studies listed are real-time architectures. This shows that concatenation continues to be a powerful method in lightweight architectures even to this day. To compare residual connections and dense connections, we generated over 15,000 random networks and trained them using the tiny ImageNet dataset. This is similar to the approach taken in the RegNet and ResNet papers. We created various search spaces based on block design, computation budget, and training recipe. In every case, we found that skip connections using concatenation were superior. We revised the architecture to revive DenseNet. Our model is named RDNet. The key characteristic of RDNet is the use of additional transition layers within each stage. This brings substantial performance advantages. We observed an impressive 1.5% increase in accuracy. Additionally, when the growth rate or width increases, it limits the size of the intermediate feature dimension, thereby resolving DenseNet's notorious large memory consumption issue. RDNet is wider and shallower compared to the DenseNet, which allows for faster inference speeds. Additionally, RDNet achieved a 0.9% accuracy improvement through the use of modernized blocks. From now, I would like to show you the changes we implemented to develop RDNet. First, to accelerate DenseNet 201, we increased the growth rate to expand the width and reduce the number of layers per stage from 6, 12, 48, 32 to 3, 3, 12, 3. Through this, the top 1 accuracy remained almost unchanged while the inference latency for a single batch improved by 4 times. The optimal depth was determined through various ablation studies. Next, we modernized the feature mixer block. Thanks to depth-wise convolution, the flops were significantly reduced, and the top 1 accuracy increased by 0.9%. We explored various kernel sizes and structures, and found that the same structure as ConvNext was optimal for RDNet as well. Next, we applied the structure of an inverted bottleneck. Due to the characteristics of dense connections, the number of channels for the input features fed into the first convolution layer is quite large. The following linear layer receives these large-sized channels and outputs feature maps with channels equal to 4 times the growth rate. In this structure, we identified a performance bottleneck and adjusted the block so that the linear layer outputs channels 4 times the number of input feature channels. This adjustment increases the computation, so we changed the growth rate from 120 to 60. We have discovered that a significant amount of the model's computation originates from the large intermediate feature that results from concatenation. To suppress the feature dimension, we introduced a transition layer every 3 dense layers. This is key feature of RDNet, achieves a 1.5% performance improvement, and resolves memory issues related to width scaling and input image scaling. Subsequently, we gained further computational advantages through patchification and achieved additional performance improvements by applying layer norm to the transition layer. By incorporating channel rescaling techniques like layer scale, we created the RDNet. Our RDNet retains all the advantages of DenseNet while brilliantly resolving its issues. Please refer to the figure on the far left. When comparing various models trained on 224 image resolution, both DenseNet and RDNet, utilizing dense connections, show robustness based on image size. The middle and right figures demonstrate RDNet has stabilized latency and memory increases compared to the original DenseNet when varying image sizes. In addition, our CKA analysis revealed that RDNet produced a significantly diverse range of features compared to ConvNext. Despite having similar block structures, RDNet and ConvNext generated different features. We suspect that the robustness of models like DenseNet and RDNet may be attributed to their ability to extract such diverse features. RDNet model family exhibits performance on par with latest CNN and ViT models. In conclusion, we revisited DenseNet and found that its concatenation shortcuts are more effective than ResNet-style additions by pilot study. By updating DenseNet with modern elements, we proved it can still compete with the latest architectures. Our RDNet outperformed mainstream architectures such as Swin Transformer, ConvNext, and DEIT3. We hope this encourages more use of concatenation in network design and shows that DenseNet can still be a strong contender alongside ResNet.